Chapter 5 of Mysticism and Logic and Other Essays by Bertrand Russell. This LibriVox recording is in the public domain. Recording by Landon D.C. Elkind at the University of Iowa in Iowa City, Iowa. Mathematics and the Metaphysicians. The 19th century, which prided itself upon the invention of steam and evolution, might have derived a more legitimate title to fame from the discovery of pure mathematics. This science, like most others, was baptized long before it was born, and thus we find writers before the 19th century alluding to what they called pure mathematics. But if they had been asked what this subject was, they would only have been able to say that it consisted of arithmetic, algebra, geometry, and so on. As to what these studies had in common, and as to what distinguished them from applied mathematics, our ancestors were completely in the dark. Pure mathematics was discovered by Boole, in a work which he called The Laws of Thought, 1854. This work abounds in asseverations that it was not mathematical, the fact being that Boole was too modest to suppose his book the first ever written on mathematics. He was also mistaken in supposing that he was dealing with the laws of thought. The question how people actually think was quite irrelevant to him, and if his book had really contained the laws of thought, it was curious that no one should ever have thought in such a way before. His book was in fact concerned with formal logic, and this is the same thing as mathematics. Pure mathematics consists entirely of assertions to the effect that, if such and such a proposition is true of anything, then such and such another proposition is true of that thing. It is essential not to discuss whether the first proposition is really true, and not to mention what the anything is, of which it is supposed to be true. Both these points would belong to applied mathematics. We start in pure mathematics from certain rules of inference, by which we can infer that if one proposition is true, then so is some other proposition. These rules of inference constitute the major part of the principles of formal logic. We then take any hypothesis that seems amusing and deduce its consequences. If our hypothesis is about anything, and not about some one or more particular things, then our deductions constitute mathematics. Thus, mathematics may be defined as the subject in which we never know what we are talking about, nor whether what we are saying is true. People who have been puzzled by the beginnings of mathematics will, I hope, find comfort in this definition, and will probably agree that it is accurate. As one of the chief triumphs of modern mathematics consists in having discovered what mathematics really is, a few more words on this subject may not be amiss. It is common to start any branch of mathematics, for instance geometry, with a certain number of primitive ideas, supposed incapable of definition, and a certain number of primitive propositions or axioms, supposed incapable of proof. Now the fact is that, though there are indefinables and indemonstrables in every branch of applied mathematics, there are none in pure mathematics, except such as belong to general logic. Logic, broadly speaking, is distinguished by the fact that its propositions can be put into a form in which they apply to anything whatever. All pure mathematics, arithmetic, analysis, and geometry, is built up by combinations of the primitive ideas of logic, and its propositions are deduced from the general axioms of logic, such as the syllogism and the other rules of inference. And this is no longer a dream or an aspiration. On the contrary, over the greater and more difficult part of the domain of mathematics, it has already been accomplished. In the few remaining cases, there is no special difficulty, and it is now being rapidly achieved. Philosophers have disputed for ages whether such deduction was possible. Mathematicians have sat down and made the deduction. For the philosophers there is now nothing left but graceful acknowledgments. The subject of formal logic, which has thus at last shown itself to be identical with mathematics, was, as everyone knows, invented by Aristotle, and formed the chief study, other than theology, of the Middle Ages. But Aristotle never got beyond the syllogism, which is a very small part of the subject, and the schoolmen never got beyond Aristotle. If any proof were required of our superiority to the medieval doctors, it might be found in this. Throughout the Middle Ages, almost all the best intellects devoted themselves to formal logic, whereas in the 19th century only an infinitesimal proportion of the world's thought went into this subject. Nevertheless, in each decade since 1850, more has been done to advance the subject than in the whole period from Aristotle to Leibniz. People have discovered how to make reasoning symbolic, as it is in algebra, so that deductions are effected by mathematical rules. They have discovered many rules besides the syllogism, and a new branch of logic, called the logic of relatives (footnote 1). This subject is due in the main to Mr. C.S. Peirce. (footnote 1). Has been invented to deal with topics that wholly surpassed the powers of the old logic, though they form the chief contents of mathematics. It is not easy for the lay mind to realize the importance of symbolism in discussing the foundations of mathematics, and the explanation may perhaps seem strangely paradoxical. The fact is that symbolism is useful because it makes things difficult. This is not true of the advanced parts of mathematics, but only of the beginnings. What we wish to know is, what can be deduced from what? Now, in the beginnings, everything is self-evident. It is very hard to see whether one self-evident proposition follows from another or not. Obvious is always the enemy to correctness. Hence we invent some new and difficult symbolism in which nothing seems obvious. Then we set up certain rules for operating on the symbols, and the whole thing becomes mechanical. In this way we find out what must be taken as premises and what can be demonstrated or defined. For instance, the whole of arithmetic and algebra has been shown to require 3 indefinable notions and 5 indemonstrable propositions. But without a symbolism, it would have been very hard to find this out. It is so obvious that 2 and 2 are 4 that we can hardly make ourselves sufficiently skeptical to doubt whether it can be proved. And the same holds in other cases where self-evident things are to be proved. But the proof of self-evident propositions may seem to the uninitiated a somewhat frivolous occupation. To this we might reply that it is often by no means self-evident that one obvious proposition follows from another obvious proposition, so that we are really discovering new truths when we prove what is evident by a method which is not evident. But a more interesting retort is that since people have tried to prove obvious propositions, they have found that many of them are false. Self-evidence is often a mere will-o'-the-wisp, which is sure to lead us astray if we take it as our guide. For instance, nothing is plainer than that a whole always has more terms than a part, or that a number is increased by adding one to it. But these propositions are now known to be usually false. Most numbers are infinite, and if a number is infinite, you may add ones to it as long as you like, without disturbing it in the least. One of the merits of a proof is that it instills a certain doubt as to the result proved. And when what is obvious can be proved in some cases, but not in others, it becomes possible to suppose that in these other cases it is false. The great master of the art of formal reasoning among the men of our own day is an Italian, Professor Piano of the University of Turin. (Footnote 1). I ought to have added Frege, but his writings were unknown to me when this article was written. Note added in 1917. End of footnote 1. He has reduced the greater part of mathematics, and he or his followers will in time have reduced the whole, to strict symbolic form, in which there are no words at all. In the ordinary mathematical books there are no doubt fewer words than most readers would wish. Still, little phrases occur, such as therefore, let us assume, consider, or hence it follows. All these, however, are a concession, and are swept away by Professor Peano. For instance, if we wish to learn the whole of arithmetic, algebra, the calculus, and indeed all that is usually called pure mathematics, except geometry, we must start with a dictionary of 3 words. One symbol stands for zero, another for number, and a third for next after. What these ideas mean it is necessary to know if you wish to become an arithmetician. But after the symbols have been invented for these 3 ideas, not another word is required in the whole development. All future symbols are symbolically explained by means of these 3. Even these 3 can be explained by means of the notions of relation and class. But this requires the logic of relations, which Professor Peano has never taken up. It must be admitted that what a mathematician has to know to begin with is not much. There are at most a dozen notions out of which all the notions in all pure mathematics, including geometry, are compounded. Professor Peano, who is assisted by a very able school of young Italian disciples, has shown how this may be done, and although the method which he has invented is capable of being carried a good deal further than he has carried it, the honor of the pioneer must belong to him. 200 years ago, Leibniz foresaw the science which Peano has perfected, and endeavoured to create it. He was prevented from succeeding by respect for the authority of Aristotle, whom he could not believe guilty of definite formal fallacies. But the subject which he desired to create now exists, in spite of the patronizing contempt with which his schemes have been treated by all superior persons. From this universal characteristic, as he called it, he hoped for a solution of all problems, and an end to all disputes. If controversies were to arise, he says, there would be no more need of disputation between 2 philosophers than between 2 accountants, for it would suffice to take their pens in their hands, to sit down to their desks, and to say to each other, with a friend as witness if they liked, "Let us calculate." This optimism has now appeared to be somewhat excessive. There still are problems whose solution is doubtful, and disputes which calculation cannot decide. But over an enormous field of what was formerly controversial, Leibniz's dream has become sober fact. In the whole philosophy of mathematics, which used to be at least as full of doubt as any other part of philosophy, order and certainty have replaced the confusion and hesitation which formerly reigned. Philosophers, of course, have not yet discovered this fact, and continue to write on such subjects in the old way. But mathematicians, at least in Italy, have now the power of treating the principles of mathematics in an exact and masterly manner, by means of which the certainty of mathematics extends also to mathematical philosophy. Hence, many of the topics which used to be placed among the great mysteries, for example, the natures of infinity, of continuity, of space, time, and motion, are now no longer in any degree open to doubt or discussion. Those who wish to know the nature of these things need only read the works of such men as Peano or Georg Cantor. They will there find exact and indubitable expositions of all these quantum mysteries. In this capricious world, nothing is more capricious than posthumous fame. One of the most notable examples of posterity's lack of judgment is the Eleatic Zeno. This man, who may be regarded as the founder of the philosophy of infinity, appears in Plato's Parmenides in the privileged position of instructor to Socrates. He invented 4 arguments, all immeasurably subtle and profound, to prove that motion is impossible, that Achilles can never overtake the tortoise, and that an arrow in flight is really at rest. After being refuted by Aristotle and by every subsequent philosopher from that day to our own, these arguments were reinstated and made the basis of a mathematical renaissance by a German professor who probably never dreamed of any connection between himself and Zeno. Weierstrass, footnote 1, professor of mathematics in the University of Berlin. He died in 1897. End of footnote 1. By strictly banishing from mathematics the use of infinitesimals, has at last shown that we live in an unchanging world. and that the arrow in its flight is truly at rest. Zeno's only error lay in inferring, if he did infer, that, because there is no such thing as a state of change, therefore the world is in the same state at any one time as at any other. This is a consequence which by no means follows, and in this respect the German mathematician is more constructive than the ingenious Greek. Weierstrass has been able, by embodying his views in mathematics, where familiarity with truth eliminates the vulgar prejudices of common sense, to invest Zeno's paradoxes with the respectable air of platitudes. And if the result is less delightful to the lover of reason than Zeno's bold defiance, it is at any rate more calculated to appease the mass of academic mankind. Zeno was concerned, as a matter of fact, with three problems, each presented by motion, but each more abstract than motion and capable of a purely arithmetical treatment. These are the problems of the infinitesimal, the infinite, and continuity. To state clearly the difficulties involved was to accomplish perhaps the hardest part of the philosopher's task. This was done by Zeno. From him to our own day the finest intellects of each generation in turn attacked the problems, but achieved, broadly speaking, nothing. In our own time, however, three men, Weierstrass, Dedekind, and Cantor, have not merely advanced the three problems, but have completely solved them. The solutions for those acquainted with mathematics are so clear as to leave no longer the slightest doubt or difficulty. This achievement is probably the greatest of which our age has to boast, and I know of no age, except perhaps the golden age of Greece, which has a more convincing proof to offer of the transcendent genius of its great men. Of the three problems, that of the infinitesimal was solved by Weierstrass. The solution of the other two was begun by Dedekind and definitively accomplished by Cantor. The infinitesimal played formerly a great part in mathematics. It was introduced by the Greeks, who regarded a circle as differing infinitesimally from a polygon with a very large number of very small equal sides. It gradually grew in importance until, when Leibniz invented the infinitesimal calculus, it seemed to become the fundamental notion of all higher mathematics. Carlyle tells us in his Frederick the Great how Leibniz used to discourse to Queen Sophia Charlotte of Prussia concerning the infinitely little, and how she would reply that on that subject she needed no instruction, the behaviour of courtiers had made her thoroughly familiar with it. But philosophers and mathematicians, who for the most part had less acquaintance with courts, continued to discuss this topic, though without making any advance. The calculus required continuity, but continuity was supposed to require the infinitely little, but nobody could discover what the infinitely little might be. It was plainly not quite zero, because a sufficiently large number of infinitesimals, added together, were seen to make up a finite whole. But nobody could point out any fraction which was not zero, yet not finite. Thus there was deadlock. But at last Weierstrass discovered that the infinitesimal was not needed at all, and that everything could be accomplished without it. Thus there was no longer any need to suppose that there was such a thing. Nowadays, therefore, mathematicians are more dignified than Leibniz. Instead of talking about the infinitely small, they talk about the infinitely great, a subject which, however appropriate to monarchs, seems unfortunately to interest them even less than the infinitely little interested the monarchs to whom Leibniz discoursed. The banishment of the infinitesimal has all sorts of odd consequences, to which one has to become gradually accustomed. For example, there is no such thing as the next moment. The interval between one moment and the next would have to be infinitesimal, since if we take two moments with a finite interval between them, there are always other moments in the interval. Thus, if there are to be no infinitesimals, no two moments are quite consecutive, but there are always other moments between any two. Hence there must be an infinite number of moments between any two, because if there were a finite number, One would be nearest the first of the two moments, and therefore next to it. This might be thought to be a difficulty, but as a matter of fact it is here that the philosophy of the infinite comes in, and makes all straight. The same sort of thing happens in space. If any piece of matter be cut in two, and then each part be halved, and so on, the bits will become smaller and smaller, and can theoretically be made as small as we please. However small they may be, they can still be cut up and made smaller still. But they will always have some finite size, however small they may be. We never reach the infinitesimal in this way, and no finite number of divisions will bring us to points. Nevertheless, there are points, only these are not to be reached by successive divisions. Here again the philosophy of the infinite shows us how this is possible, and why points are not infinitesimal lengths. As regards motion and change, we get similarly curious results. People used to think that when a thing changes, it must be in a state of change, and that when a thing moves, it is in a state of motion. This is now known to be a mistake. When a body moves, all that can be said is that it is in one place at one time, and in another at another. We must not say that it will be in a neighboring place at the next instant, since there is no next instant. Philosophers often tell us that when a body is in motion, it changes its position within the instant. To this view, Zeno long ago made the fatal retort that every body always is where it is. But a retort so simple and brief was not of the kind to which philosophers are accustomed to give weight, and they have continued down to our own day to repeat the same phrases which roused the Eleatic's destructive ardor. It was only recently that it became possible to explain motion in detail in accordance with Zeno's platitude, and in opposition to the philosopher's paradox. We may now at last indulge the comfortable belief that a body in motion is just as truly where it is as a body at rest. Motion consists merely in the fact that bodies are sometimes in one place and sometimes in another, and that they are at intermediate places at intermediate times. Only those who have waded through the quagmire of philosophic speculation on this subject can realize what a liberation from antique prejudices is involved in this simple and straightforward commonplace. The philosophy of the infinitesimal, as we have just seen, is mainly negative. People used to believe in it, and now they have found out their mistake. The philosophy of the infinite, on the other hand, is wholly positive. It was formerly supposed that infinite numbers and the mathematical infinite generally were self-contradictory. But as it was obvious that there were infinities, for example the number of numbers, the contradictions of infinity seemed unavoidable, and philosophy seemed to have wandered into a cul-de-sac. This difficulty led to Kant's antinomies, and hence, more or less indirectly, to much of Hegel's dialectic method. Almost all current philosophy is upset by the fact, of which very few philosophers are as yet aware, that all the ancient and respectable contradictions in the notion of the infinite have been once for all disposed of. The method by which this has been done is most interesting and instructive. In the first place, though people had talked glibly about infinity ever since the beginnings of Greek thought, nobody had ever thought of asking, what is infinity? If any philosopher had been asked for a definition of infinity, he might have produced some unintelligible rigmarole, but he would certainly not have been able to give a definition that had any meaning at all. 20 years ago, roughly speaking, Dedekind and Cantor asked this question, and, what is more remarkable, they answered it. They found, that is to say, a perfectly precise definition of an infinite number or an infinite collection of things. This was the first, and perhaps the greatest, step. It then remained to examine the supposed contradictions in this notion. Hence Cantor proceeded in the only proper way. He took pairs of contradictory propositions, in which both sides of the contradiction would be usually regarded as demonstrable, and he strictly examined the supposed proofs. He found that all proofs adverse to infinity involved a certain principle, at first sight obviously true, but destructive in its consequences of almost all mathematics. The proofs favourable to infinity, on the other hand, involved no principle that had evil consequences. It thus appeared that common sense had allowed itself to be taken in by a specious maxim, and that, when once this maxim was rejected, all went well. The maxim in question is that if one collection is part of another, the one which is a part has fewer terms than the one of which it is a part. This maxim is true of finite numbers. For example, Englishmen are only some among Europeans, and there are fewer Englishmen than Europeans. But when we come to infinite numbers, this is no longer true. The breakdown of the maxim gives us the precise definition of infinity. A collection of terms is infinite when it contains as parts other collections which have just as many terms as it has. If you can take away some of the terms of a collection without diminishing the number of terms, then there are an infinite number of terms in the collection. For example, there are just as many even numbers as there are numbers altogether, since every number can be doubled. This may be seen by putting odd and even numbers together in one row, and even numbers alone in a row below. 1, 2, 3, 4, 5 to infinity, 2, 4, 6, 8, 10 to infinity. There are obviously just as many numbers in the row below as in the row above, because there is one below for each one above. This property, which was formerly thought to be a contradiction, is now transformed into a harmless definition of infinity, and shows in the above case that the number of finite numbers is infinite. But the uninitiated may wonder how it is possible to deal with a number which cannot be counted. It is impossible to count up all the numbers one by one because, however many we may count, there are always more to follow. The fact is that counting is a very vulgar and elementary way of finding out how many terms there are in a collection. And in any case, counting gives us what mathematicians call the ordinal number of our terms. That is to say, it arranges our terms in an order or series, and its result tells us what type of series results from this arrangement. In other words, it is impossible to count things without counting some first and others afterward, so that counting always has to do with order. Now, when there are only a finite number of terms, we can count them in any order we like. But when there are an infinite number, what corresponds to counting will give us quite different results according to the way in which we carry out the operation. Thus the ordinal number, which results from what in a general sense may be called counting, depends not only upon how many terms we have, but also, where the number of terms is infinite, upon the way in which the terms are arranged. The fundamental infinite numbers are not ordinal, but are what is called cardinal. They are not obtained by putting our terms in order and counting them, but by a different method, which tells us, to begin with, whether two collections have the same number of terms, or, if not, which is the greater. Footnote 1. Note added in 1917. Although some infinite numbers are greater than some others, it cannot be proved that of any two infinite numbers, one must be the greater. End of footnote 1. It does not tell us, in the way in which counting does, what number of terms a collection has. But if we define a number as the number of terms in such and such a collection, then this method enables us to discover whether some or other collection that may be mentioned has more or fewer terms. An illustration will show how this is done. If there existed some country in which, for one reason or another, it was impossible to take a census, but in which it was known that every man had a wife and every woman a husband, then, provided polygamy was not a national institution, we should know without counting that there were exactly as many men as there were women in that country. neither more nor less. This method can be applied generally. If there is some relation which, like marriage, connects the things in one collection each with one of the things in another collection, and vice versa, then the two collections have the same number of terms. This was the way in which we found that there are as many even numbers as there are numbers. Every number can be doubled, and every even number can be halved, and each process gives just one number corresponding to the one that is doubled or halved. And in this way we can find any number of collections, each of which has just as many terms as there are finite numbers. If every term of a collection can be hooked on to a number, and all the finite numbers are used once and only once in the process, then our collection must have just as many terms as there are finite numbers. This is the general method by which the numbers of infinite collections are defined. But it must not be supposed that all infinite numbers are equal. On the contrary, there are infinitely more infinite numbers than finite ones. There are more ways of arranging the finite numbers in different types of series than there are finite numbers. There are probably more points in space and more moments in time than there are finite numbers. There are exactly as many fractions as whole numbers, although there are an infinite number of fractions between any two whole numbers. But there are more irrational numbers than there are whole numbers or fractions. There are probably exactly as many points in space as there are irrational numbers, and exactly as many points on a line a millionth of an inch long as in the whole of infinite space. There is a greatest of all infinite numbers, which is the number of things altogether, of every sort and kind. It is obvious that there cannot be a greater number than this because, if everything has been taken, there is nothing left to add. Cantor has a proof that there is no greatest number, and if this proof were valid, the contradictions of infinity would reappear in a sublimated form. But in this one point the master has been guilty of a very subtle fallacy, which I hope to explain in some future work. Footnote 1. Cantor was not guilty of a fallacy on this point. His proof that there is no greatest number is valid. The solution of the puzzle is complicated and depends upon the theory of types, which is explained in Principia Mathematica, Volume 1, Cambridge University Press, 1910. Note added in 1917. End of footnote 1. We can now understand why Zeno believed that Achilles cannot overtake the tortoise, and why, as a matter of fact, he can overtake it. We shall see that all the people who disagreed with Zeno had no right to do so, because they all accepted premises from which his conclusion followed. The argument is this. Let Achilles and the tortoise start along a road at the same time, the tortoise, as is only fair, being allowed a handicap. Let Achilles go twice as fast as the tortoise, or 10 times or 100 times as fast. Then he will never reach the tortoise. For at every moment the tortoise is somewhere, and Achilles is somewhere. And neither is ever twice in the same place while the race is going on. Thus the tortoise goes to just as many places as Achilles does, because each is in one place at one moment, and in another at any other moment. But if Achilles were to catch up with the tortoise, the places where the tortoise would have been would be only part of the places where Achilles would have been. Here we must suppose Zeno appealed to the maxim that the whole has more terms than the part. Footnote 2. This must not be regarded as a historically correct account of what Zeno actually had in mind. It is a new argument for his conclusion, not the argument which influenced him. On this point, see, for example, C.D. Broad, Note on Achilles and the Tortoise. Mind, New Style, Volume 22, pages 318 to 319. Much valuable work on the interpretation of Zeno has been done since this article was written. Note added in 1917. End of footnote 2. Thus, if Achilles were to overtake the tortoise, he would have been in more places than the tortoise. But we saw that he must, in any period, be in exactly as many places as the tortoise. Hence we infer that he can never catch the tortoise. This argument is strictly correct if we allow the axiom that the whole has more terms than the part. As the conclusion is absurd, the axiom must be rejected, and then all goes well. But there is no good word to be said for the philosophers of the past 2000 years and more who have all allowed the axiom and denied the conclusion. The retention of this axiom leads to absolute contradictions, while its rejection leads only to oddities. Some of these oddities, it must be confessed, are very odd. One of them, which I shall call the paradox of Tristram Shandy, is the converse of the Achilles, and shows that the tortoise, if you give him time, will go just as far as Achilles. Tristram Shandy, as we know, employed 2 years in chronicling the first 2 days of his life, and lamented that, at this rate, material would accumulate faster than he could deal with it, so that, as years went by, he would be farther and farther from the end of his history. Now I maintain that, if he had lived forever, and had not wearied of the task, then, even if his life had continued as eventfully as it began, no part of his biography would have remained unwritten. For consider, the 100th day will be described in the 100th year, the 1000th in the 1000th year, and so on. Whatever day we may choose as so far on that he cannot hope to reach it, that day will be described in the corresponding year. Thus any day that may be mentioned will be written up sooner or later, and therefore no part of the biography will remain permanently unwritten. This paradoxical but perfectly true proposition depends upon the fact that the number of days in all time is no greater than the number of years. Thus, on the subject of infinity, it is impossible to avoid conclusions which at first sight appear paradoxical, and this is the reason why so many philosophers have supposed that there were inherent contradictions in the infinite. But a little practice enables one to grasp the true principles of Cantor's doctrine, and to acquire new and better instincts as to the true and the false. The oddities then become no odder than the people at the antipodes, who used to be thought impossible because they would find it so inconvenient to stand on their heads. The solution of the problems concerning infinity has enabled Cantor to solve also the problems of continuity. Of this, as of infinity, he has given a perfectly precise definition, and has shown that there are no contradictions in the notions so defined. But this subject is so technical that it is impossible to give any account of it here. The notion of continuity depends upon that of order, since continuity is merely a particular type of order. Mathematics has, in modern times, brought order into greater and greater prominence. In former days it was supposed, and philosophers are still apt to suppose, that quantity was the fundamental notion of mathematics. But nowadays quantity is banished altogether, except from one little corner of geometry, while order more and more reigns supreme. The investigation of different kinds of series and their relations is now a very large part of mathematics, and it has been found that this investigation can be conducted without any reference to quantity, and for the most part without any reference to number. All the types of series are capable of formal definition, and their properties can be deduced from the principles of symbolic logic by means of the algebra of relatives. The notion of a limit, which is fundamental in the greater part of higher mathematics, used to be defined by means of quantity, as a term to which the terms of some series approximate as nearly as we please. But nowadays the limit is defined quite differently, and the series which it limits may not approximate to it at all. This improvement also is due to Cantor, and it is one which has revolutionized mathematics. Only order is now relevant to limits. Thus, for instance, the smallest of the infinite integers is the limit of the finite integers, though all finite integers are at an infinite distance from it. The study of different types of series is a general subject of which the study of ordinal numbers mentioned above is a special and very interesting branch. but the unavoidable technicalities of this subject render it impossible to explain to any but professed mathematicians. Geometry, like arithmetic, has been subsumed in recent times under the general study of order. It was formerly supposed that geometry was the study of the nature of the space in which we live, and accordingly it was urged, by those who held that what exists can only be known empirically, that geometry should really be regarded as belonging to applied mathematics. But it has gradually appeared, by the increase of non-Euclidean systems, that geometry throws no more light upon the nature of space than arithmetic throws upon the population of the United States. Geometry is a whole collection of deductive sciences based on a corresponding collection of sets of axioms. One set of axioms is Euclid's. Other equally good sets of axioms lead to other results. Whether Euclid's axioms are true is a question as to which the pure mathematician is indifferent, and, what is more, it is a question which it is theoretically impossible to answer with certainty in the affirmative. It might possibly be shown, by very careful measurements, that Euclid's axioms are false, but no measurements could ever assure us, owing to the errors of observation, that they are exactly true. Thus the geometer leaves to the man of science to decide, as best he may, what axioms are most nearly true in the actual world. The geometer takes any set of axioms that seem interesting, and deduces their consequences. What defines geometry in this sense is that the axioms must give rise to a series of more than one dimension, and it is thus that geometry becomes a department in the study of order. In geometry, as in other parts of mathematics, Peano and his disciples have done work of the very greatest merit as regards principles. Formerly, it was held by philosophers and mathematicians alike that the proofs in geometry depended on the figure. Nowadays, this is known to be false. In the best books, there are no figures at all. The reasoning proceeds by the strict rules of formal logic from a set of axioms laid down to begin with. If a figure is used, all sorts of things seem obviously to follow, which no formal reasoning can prove from the explicit axioms, and which, as a matter of fact, are only accepted because they are obvious. By banishing the figure, it becomes possible to discover all the axioms that are needed, and in this way all sorts of possibilities which would have otherwise remained undetected are brought to light. One great advance from the point of view of correctness has been made by introducing points as they are required, and not starting, as was formerly done, by assuming the whole of space. This method is due partly to Peano, partly to another Italian named Fano. To those unaccustomed to it, it has an air of somewhat wilful pedantry. In this way, we begin with the following axioms. 1. There is a class of entities called points. 2. There is at least one point. 3. If A be a point, there is at least one other point besides A. Then we bring in the straight line joining 2 points and begin again with 4, namely, on the straight line joining A and B, there is at least one other point besides A and B. 5. There is at least one point not on the line AB. And so we go on till we have the means of obtaining as many points as we require. But the word space, as Peano humorously remarks, is one for which geometry has no use at all. The rigid methods employed by modern geometers have deposed Euclid from his pinnacle of correctness. It was thought, until recent times, that, as Sir Henry Savile remarked in 1621, there were only 2 blemishes in Euclid, the theory of parallels and the theory of proportion. It is now known that these are almost the only points in which Euclid is free from blemish. Countless errors are involved in his first 8 propositions. That is to say, not only is it doubtful whether his axioms are true, which is a comparatively trivial matter, but it is certain that his propositions do not follow from the axioms which he enunciates. A vastly greater number of axioms which Euclid unconsciously employs are required for the proof of his propositions. Even in the first proposition of all, where he constructs an equilateral triangle on a given base, he uses two circles which are assumed to intersect, but no explicit axiom assures us that they do so, and in some kinds of spaces they do not always intersect. It is quite doubtful whether our space belongs to one of these kinds or not. Thus Euclid fails entirely to prove his point in the very first proposition. As he is certainly not an easy author, and is terribly long-winded, he has no longer any but unhistorical interest. Under these circumstances, it is nothing less than a scandal that he should still be taught to boys in England. Footnote 1. Since the above was written, he has ceased to be used as a textbook, but I fear many of the books now used are so bad that the change is no great improvement. Note added in 1917. End of footnote 1. A book should have either intelligibility or correctness. To combine the two is impossible, but to lack both is to be unworthy of such a place as Euclid has occupied in education. The most remarkable result of modern methods in mathematics is the importance of symbolic logic and of rigid formalism. Mathematicians under the influence of Weierstrass have shown in modern times a care for accuracy and an aversion to slipshod reasoning, such as had not been known among them previously since the time of the Greeks. The great inventions of the 17th century, analytical geometry and the infinitesimal calculus, were so fruitful in new results that mathematicians had neither time nor inclination to examine their foundations. Philosophers who should have taken up the task had too little mathematical ability to invent the new branches of mathematics which have now been found necessary for any adequate discussion. Thus mathematicians were only awakened from their dogmatic slumbers when Weierstrass and his followers showed that many of their most cherished propositions are in general false. Macaulay, contrasting the certainty of mathematics with the uncertainty of philosophy, asks, "Who ever heard of a reaction against Taylor's theorem?" If he had lived now, he himself might have heard of such a reaction, for this is precisely one of the theorems which modern investigations have overthrown. Such rude shocks to mathematical faith have produced that love of formalism which appears, to those who are ignorant of its motive, to be mere outrageous pedantry. The proof that all mathematics, including geometry, is nothing but formal logic is a fatal blow to the Kantian philosophy. Kant, rightly perceiving that Euclid's propositions could not be deduced from Euclid's axioms without the help of figures, invented a theory of knowledge to account for this fact, and it accounted so successfully that, when the fact is shown to be a mere defect in Euclid and not a result of the nature of geometrical reasoning, Kant's theory also has to be abandoned. The whole doctrine of a priori intuitions by which Kant explained the possibility of pure mathematics is wholly inapplicable to mathematics in its present form. The Aristotelian doctrines of the schoolmen come nearer in spirit to the doctrines which modern mathematics inspire, but the schoolmen were hampered by the fact that their formal logic was very defective, and that the philosophical logic based upon the syllogism showed a corresponding narrowness. What is now required is to give the greatest possible development to mathematical logic, to allow to the full the importance of relations, and then to found upon this secure basis a new philosophical logic, which may hope to borrow some of the exactitude and certainty of its mathematical foundation. If this can be successfully accomplished, there is every reason to hope that the near future will be as great an epoch in pure philosophy as the immediate past has been in the principles of mathematics. Great triumphs inspire great hopes, and pure thought may achieve within our generation such results as will place our time in this respect on a level with the greatest age of Greece. Footnote 1. The greatest age of Greece was brought to an end by the Peloponnesian War. Note added in 1917. End of footnote 1. End of chapter 5.